Welcome back to The Explainer. I am so thrilled to have you here today. Look, if you're the kind of focused learner who wants to get straight to the core of how things actually work, well, you're in exactly the right place. Today, we're going to totally demystify those massive, just mind-bogglingly complex systems that actually keep the lights on in our homes and our cities. We're going to follow the flow of power, tracing its incredible journey from raw mechanical creation inside the plant all the way out to the national grid. It's literally an absolute marvel of engineering, and we're breaking it down slide by slide so you can perfectly visualize the magic behind your wall outlet.
Okay, let's dive right into this. We've got a clear roadmap today with 5 main stops. First, the anatomy of a generator. Second, the excitation system explained. Third, cooling the generator. Fourth, the Powerformer revolution. And finally, transformers and the grid.
So starting off with Section 1, anatomy of a generator, which is really the heart of the plant.
You can really think of the generator as the biological heart of the whole power plant. This is exactly where the magic happens, where raw mechanical rotation from a giant turbine is actually transformed into raw electrical energy. Now, just looking at this map of the connections, the synchronous generator is, without a doubt, the most crucial element in this entire electrical division. You can see how it connects outward to both the main step-up transformer and the auxiliary transformer. But notice those external source connections on there too? Those are absolutely vital. Because, think about it, if the generator goes offline, the plant's auxiliary systems still need power. That means the generator can't just bring itself back to life without an external boost from the grid or maybe an emergency diesel generator. It's like needing a jump start for your car, but on a massive scale.
And this brilliantly illustrates the 2 main physical components of a synchronous generator. On the left, you've got the stator. It's built from these isolated silicon steel sheets, and those slots you're seeing, that is where the stator windings are placed. The stator is completely stationary, and this is where the actual electrical power is generated. Then, on the right side, we have the rotor. Now, this is a massive piece of machinery that's directly connected to the turbine, which means it spins fast. The rotor carries the magnetic field. So as the rotor spins its magnetic field inside that stationary stator, it basically cuts across those windings and boom, electrical voltage is born.
But wait, to actually make that work, we need something called field current. See, the rotor doesn't just naturally have a magnetic field strong enough to power an entire city. We have to create it. And we do this by applying a direct current, a DC voltage, directly to the rotor using these things called carbon brushes. This direct current forms the incredibly powerful magnetic field that is absolutely necessary for the spinning rotor to induce electricity over in the stator.
Moving on to Section 2, the Excitation System Explained, or what we can call the nervous system of the plant. Now, to manage that crucial field current we were just talking about, we need a really complex nervous system. But right here, we actually run into a totally fascinating engineering riddle. Which came first, the chicken or the egg? Seriously, think about it. The device that provides the DC current to the rotor is called the exciter, but in normal operation, the exciter gets its power from the main generator. So, if the exciter needs power from the main generator to create the magnetic field, but the generator needs the magnetic field to actually make power, how on earth does this whole system start up from zero?
Well, the answer is this really elegant 3-step starting process. Step 1, we bring in a completely independent third element called a permanent magnet generator, or PMG for short. This is a much smaller generator sitting on the exact same shaft, but it has strong permanent magnets already built in, meaning it doesn't need external power to have a magnetic field. Pretty clever, right? Step 2, as the shaft starts spinning, the PMG creates a small initial current and feeds it right into the exciter. And then step 3, the exciter takes that little initial spark, ramps it way up, and supplies a massive DC current. We're talking sometimes around 5,000 amps straight into the main generator's field. Once the main generator is finally up and running, it takes over feeding the exciter, and the PMG's job is basically done. Riddle solved.
So the crucial point here is, we don't just need to start the magnetic field, we have to precisely control it at all times. And this is done by the AVR, the Automatic Voltage Regulator. The AVR basically acts as a high-speed electronic brain for the whole operation. If it senses even a tiny drop in the generator's output voltage, it instantly adjusts the firing angle of thyristors, which you can just think of as really high-speed electronic switches. This increases the DC current flowing into the rotor, which strengthens the magnetic field, which instantly boosts the voltage right back to normal. It literally reacts in fractions of a second to keep your power completely stable.
All right, that brings us to Section 3, cooling the generator. Think of this as the lungs.
As you can imagine, spinning massive metal rotors and pushing thousands of amps creates an absolutely astronomical amount of heat. And if we don't actively remove that heat, the entire plant will literally melt down.
So to act as the lungs of the plant, engineers typically use two highly specialized cooling methods. First up is demineralized water, or demi-water. Because it's had all its minerals completely stripped out, it doesn't conduct electricity at all. That makes it perfect for flowing directly through the stator windings to carry heat away safely. But the really big player here is hydrogen. Hydrogen gas is used to cool the main generator enclosure because it has exceptionally high thermal conductivity, way better than almost any other gas, and it acts as a fantastic electrical insulator.
Now, what's really interesting, and frankly a little terrifying about this, is the sheer danger involved. You're looking at a bank of hydrogen cylinders used in a real power plant. While hydrogen is a fantastic coolant, it's also incredibly volatile. Our source points out that if hydrogen mixes with even 14% oxygen within that enclosed generator space, it becomes highly explosive. No joke. Because of this, the generator is completely sealed off from oxygen, and the plant has severe, heavy-duty safety measures in place. If any kind of fault occurs, there are these massive vents designed to immediately purge the hydrogen right outside into the open air to prevent a catastrophic explosion.
Okay, let's shift gears to Section 4, the Powerformer revolution. This is where we start changing the game.
Up until the late 90s, the physical layout of power plants had been pretty much exactly the same for decades. For years, traditional generators output power at a relatively low voltage. That meant every single plant absolutely required a massive step-up transformer right next to it just to boost the voltage high enough for the electrical grid. They also used these standard rectangular conductors in the stator. But then, in 1998, the Swiss company ABB invented something called the Powerformer. A Powerformer can actually generate high voltages directly. We're talking up to 400 kilovolts right out of the machine. This means it connects directly to the high-voltage grid, completely eliminating the need for a step-up transformer altogether. To pull this off, they replaced the old rectangular conductors with high-voltage XLPE circular cables right inside the stator.
And guys, this isn't just a neat parlor trick. It is an absolute game changer, giving us 4 massive benefits. 1, it increases overall plant efficiency by about 1.5%, which is huge at that scale. 2, it significantly lowers the total fixed costs of building the plant in the first place. 3, by ditching that step-up transformer, it totally eliminates reactive power losses, which is essentially wasted energy that usually happens inside the transformer itself. And 4, those new circular cables provide a much more even electric field distribution, which really cuts down on mechanical stress. To put all that into perspective, one study from our source looked at a 3,200 gigawatt-hour hydro plant over in India. By replacing 4 traditional generators and their step-up transformers with Powerformers, they reduced their fixed and maintenance costs by nearly 24%. Just incredible.
Let's move to our final stop and see how this all builds together in Section 5, Transformers and the Grid, the true muscle of the whole operation.
Now, while powerformers are undeniably revolutionary, the vast majority of the world's power plants still use traditional generators, and that means they rely heavily on transformers, the muscle I just mentioned, to push all that generated power out into the world. In a standard setup, you generally have 4 main types of transformers. You have the unit auxiliary transformer and the startup transformer, both of which step power down just to run the plant's own internal equipment. Then you have the excitation transformer, which feeds that critical AVR system we talked about earlier. But the absolute heavy lifter is the main step-up transformer. In a lot of large plants, this colossal machine is wired directly to the generator, sometimes without even a single circuit breaker in between, forming one massive unified generator transformer set.
And the reason I call it the heavy lifter is because of the sheer, almost unimaginable scale of its job. A traditional, massive generator usually creates power at somewhere between 15 to 23 kilovolts. But, power just can't travel hundreds of miles across the country at that voltage without losing almost all of its energy to heat. So this main step-up transformer takes that 23 kilovolts and boosts it all the way up to 220 or even 500,000 volts. It is at this massive 500 kilovolt level that the power is finally injected into the national transmission grid to make the long journey to your city.
So here's what I want you to think about. The next time you casually reach out and flip a light switch in your living room, I want you to really picture this unbelievable symphony of engineering that you just tapped into. In that exact fraction of a second, you are literally relying on carbon brushes rubbing against a massive spinning rotor, high-speed electronic brains adjusting thyristor firing angles, explosive hydrogen gas fighting off melting temperatures, and gigantic step-up transformers pushing 500,000 volts across the country. It's dangerous, it's incredibly precise, and it is just beautifully complex.
Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll see you on the next one.